Good afternoon from Japan. Yep. Welcome everyone to joining our scientific forum for Global Methane Budget 2020. My name is Pirapan Chitrapirom. I'm the Executive Director of Tsukuba GCP office. Yes, I would like to welcome you again to this forum. But before we start, I would like to just pointed out some feature of Zoom meeting that you can utilize to engage in our conversation today. So today meeting is in seminar format, right? So you could start using the chat box to introduce yourself and to have a discussion amongst yourself and also the panel while the presentation is ongoing. If you have any question and answer question that you would like to address to the panel or any speaker, please put in the Q&A box that you see below. Or the question in the Q&A box will be sent to the panel and then we will answer them accordingly. If you would like to see the subtitle function, which is just to notify you of the name of the speaker, please switch the subtitle function on. So yep, if you have any other inquiry, please also address to the panel. Yep. Thank you. So we begin with sorry. So I just want to kind of give a background to the global methane budget, right? As we know, climate change is one of the most challenging scientific and political issue of our time. And methane gas is the second most important greenhouse gas contribute to the human-induced climate change after the carbon dioxide, right? But despite this important implication, there is still much unknown and uncertainty surrounding the global methane level. For instance, we cannot accurately estimate the global methane emission on the Earth's surface, nor can we explain precisely how nature eliminates methane gases from the atmosphere. Insight into this question will help us to better understand the role of methane and their interaction with other greenhouse gases. So on July 15 this year, the Global Carbon Project published an update and most comprehensive global methane budget with all methane source and sink. It also provides insight into the geographical region and economic sector where the emission changed the most over the most recent 2 decades. So today we are coming together to learn more about this, hearing from researchers from Japan particularly. And yes, before we go into the scientific part, I would like to invite Nobuko Saikusa, Director of CH NIES, to give an opening for today, please. Thank you.
Okay, thank you very much, Pirapan-san. Good afternoon, everyone. I'm Nobuko Saikusa, Director of the Center for Global Environmental Research in NIES. I really appreciate your attendance to this science forum on the Global Methane Budget 2020, hosted by the Global Carbon Project Tsukuba International Project Office and NIES, also co-organized by JAMSTEC, Meteorological Research Institute, and Future Earth Japan Global Hub. During the past several years, I have been working with many of today's speakers among the same project under the Ministry of the Environment or working together in NIES. All the speakers today are really the leading scientists on climate change, particularly on the global warming, based on the various kinds of greenhouse gas observation, integrated data analysis, and modeling, both globally and regionally. Their scientific contributions are significant, not only for the methane-related studies, but also for fostering young scientists, disseminating research outcomes to the public, and working together with international joint projects and frameworks, such as Global Carbon Project and IPCC. I've been looking forward to this science forum very much on the Global Methane Budget 2020, where you can meet such scientists online and hear their voices directly. I hope you enjoy today's the program. Thank you very much.
Thank you very much, Saikusa-san. Next, I would like to invite Jill Sion, the interim lead research and innovation from Future Earth, to give a welcoming speech. Thank you.
Thank you very much. I want to welcome everybody that is joining us here today, and especially thank you for your time and effort in joining this event. As introduced, this event is co-organized by several organizations, and I'm here to speak today as the Interim Lead Research and Innovation of Future Earth. And I will give you a little bit of a broader background and context as of where the Global Carbon Project fits in within the broader Future Earth environment and community. So basically, we are living currently in the Anthropocene, and we have established that there are many environmental and societal changes that are happening rapidly, and they're complex and interlinked. So we cannot look at issues from a single disciplinary perspective. Under Future Earth, we have various global research projects, and as you can see here, we have the Global Carbon Project, which has been taking a leading role in this methane budget, represented here. These are the core elements within the Future Earth community, and they have been contributing disciplinary research that is essential to, on the one hand, measure, but also look at opportunities on how to improve some of these environmental and social issues around the world. Future Earth also convenes networks and on topic-based elements, convenes people to join and engage with researchers, but also together with other stakeholders and innovators from around the world to come up with some of the solutions to these complex societal problems. The focus here is again on integrating across disciplines, both in the social and natural sciences. Just to give you a recent contextual contribution on the needs for measuring all the complex issues that we are facing. So just on July 31st, we could identify that there were widespread extreme heat in the Middle East, especially in Iran, Iraq, Kuwait, and Saudi Arabia. This is one of the reasons why it's essential to have reports such as the methane budget come out for people to make better decisions on and move forward with innovation. Now, you might say, oh, there's extreme weather in some parts around the world, but why is that relevant to other places? The reason for that is that there are tipping elements, and they may have cascading effects or a domino effect on other large Earth system elements, as you can see a few examples here, where one system might collapse. It can result in a cascading catastrophic event in other places around the world. And we can identify that these issues usually do not stand alone, but they are interlinked with many other issues, such as the drivers of climate change, but also the potential results that come out of this. Now, we're talking here about methane, and we have to understand that methane is not the only greenhouse gas. There are many other elements to take into consideration. For example, we see here that methane, when we're looking at the radial forcing change during the time between 1750 and 2009, we can identify that methane has a relatively short lifetime span compared to CO2 of 9 years. And it has both a direct and indirect effect. So methane itself can cause heating, but it also has a chemical effect creating several other greenhouse gases. Another element to take into consideration here is that there's there have been some reductions in methane exhaust identified. And I will show this in this particular slide. You can see here the lifetime span of 9 years, but we're particularly looking at a shortened reduction in emissions between up until the year 2006. But after that, we can see a resumed increase. Some of the potential causes behind this are waste management changes, but also changes in agriculture practices, and the potential changes of other environmental or cultural elements. Now, bringing back the science to make an impact on society, one of the elements of Future Earth is that we try to translate the science into various ways depending on the end user. So we have communication channels that bring this to private sector, but also to a more general audience, as well as science policy interfaces where we can contribute to new policy implications. So we have here the example of the carbon budget that was also convened by GCP, the Global Carbon Project. Our executive director, Amy Lewis of Future Earth, that contributed to the high-level political forum in 2018. We have been convening, for example, 10 new insights in climate science, and have been presenting that at COP. But we are also partnering or taking on observer roles with various international and local institutions to drive this change. So once again, I want to welcome everybody, and we are looking forward very much to the expertise that will be shared in the next few presentations. Thank you very much.
Thank you, Jules. So next, let me share with you a little bit about the GCP or Global Carbon Budget, right? Okay. So the Global Carbon Budget, the Global Carbon Project, or GCP, is established in 2001. The rationale behind it is in response to the recognition that for the need for an international cooperation to facilitate the research, in the Earth carbon cycle. So no scientist from one nation can do this one alone. And our aim is to develop a complete picture of the global carbon cycle, basing on 3 research scopes: diagnostic, accounting, system insight, and identify intervention. So let me break that down for you. So here's our selected contribution. So in the diagnostic and accounting, we have the global carbon budget, the methane budget, which is what we're talking today, the nitric oxide budget, which is coming soon. And also we're looking at the urban greenhouse gas and near real-time estimation. This is also a very recent topic that we are engaging with, given the COVID situation that occurred from last year until this year, and how does that affect the urban emission. In process and intervention, we looking into the regional carbon cycle budget and process. We had a recap 2 meeting at Gotemba last year, and that project will be ongoing until 2022. Carbon management, which is the central around the Tsukuba office, we're looking at the negative emission, removal of non-CO2 greenhouse gas, regional carbon cycle assessment, and decarbonization pathway. And also with activity like today, we also engaging in the outreach and valorization, such as holding side event in UN Climate Summit, COP, and also writing blogs and global carbon atlas, and also social media. If you would like to learn more about our activity, please visit our website here, which is www.globalcarbonproject.org. So yes, let me come to the GCP outreach activity. We are trying to extending our science messages into the media more and more, given the importance of the issue that we are addressing. So from last year, the Global Carbon Budget on 2019, in which we reissued the annual update in 4th of December. And this year, we're working together with Future Earth, Jamstech, MRI, and also NIES to publish this Global Methane Budget. So here, let me present to you again the Global Methane Budget 2020. These are the 10 scientists from Japan who are contributing to this Global Methane Budget. So without further ado, let me pass on to Prabir and Shamil to talk to you more about the message of the budget itself. Thank you.
Samil, can you start?
Okay, I can start. So my name is Samil Maksutov, and I am starting this presentation together with Prabir Patra from Jamstek. I work at National Institute for Environmental Studies in using data from GOSAT satellite for the methane and CO2 emissions. And Prabir Patra is one of the members of Global Methane Budget Steering Group, and he is very well positioned to present this project. So I will go ahead, please, next slide, with introducing the contributors to this project. I should say this project started several years ago, and first budget was published 7 years ago, was under leadership of the Philippe Sier and from France and Pep Canadell from Australia. They promoted the expansion of global carbon budget into including the methane. So there was a global methane budget, first one in 2013. Now the Marielle Sanois from France is leading the actual work, and she did enormous amount of work together with their group to put together all the contributions from almost 100 people here. It was 91 contributor. So I also want to say, next slide please, Prabir, about the groups that contributed to this project. This atmospheric observation data set that many big groups, including NOAA, Earth Science Research Laboratory, has global network, A-Gauge network, and then Australian and other networks, and including also data from Japan, including NIES, GMA, and also GOSAT satellite data. We have a group that does atmospheric inversions, atmospheric modelers who actually benefit a lot from participating in this project, because they have a benchmark also to compare with each other and to improve. And we have the budget every 4 years, so there is a continuous improvement in the quality and the number of people and the data they use is increasing from project to project. We have many modelers who did simulation of wetland emissions with many ecosystem models, and this is very important part because it is used to be very much unknown, and that's much more certainty now with this component, and there will be a need, of course, for future improvement, but we already made a big progress. There is a fire emission data set. There's also a large important part is anthropogenic emission inventory. For example, EDGAR, which makes emission on gridded base, which goes to is input to the inverse modeling to atmospheric transport models. And also it's a very important benchmark to compare with national emission inventories, because every nation contributes the report of their methane emissions to United Nations, and they use the inventory guidelines which set the different type of emission factors. Some of them are default, and the EDGAR is using default factors, but many nations use their own emission factors for different emission components that they develop using their own observation. So next slide, please. So here we have the overall contribution as we see the atmospheric observation and emission inventories and biogeochemical models. And also we have estimates from methane sinks. And all this together can be used as a bottom-up estimate. So then, in addition to that, we can combine atmospheric observation with a transport modeling to derive the corrections to the bottom-up estimate, which will make it consistent to atmospheric growth rate and also global distribution of the observed concentrations. Next slide, please. So here I should give you some introduction about units. We use the units of teragram, which is 1 million ton for emissions. And we use units 1 part per billion, ppb, for the concentrations and the concentration changes. So the rough correspondence between 1 part per billion of methane added to atmosphere is 2.7 teragram methane emitted globally. So next slide, please. And very important part of this budget is the contribution to explaining the very recent event in the methane concentration time series, the history of methane. There is a growth of methane concentration that started somewhere 2006. And it's difficult to explain with the available information. For example, you can see that in 2008, when there was a Beijing Olympic, there was already effort to reduce pollution, to switch in China from coal to natural gas. So people would expect there will be less growth and there would be some constraint on the anthropogenic emissions, but still we have a growth. Of course, world economy is growing, but still assigning this growth to particular source is difficult. We can expect wetlands are emitting more because of global warming. We can expect there was more agricultural production, and there are a lot of uncertainties. So we have to put together contribution from many specialists, experts in their fields to give an overall view. The next slide, please. Well, talking on observation, here you see the maps of available observations, and there are like red dots are ground-based observation, and green dots are satellite observation by Japanese GOSAT satellite. This is the only satellite that covers that long period of 2009 to 2017. That is half of the analysis period, and we were very lucky that this satellite stayed on orbit for almost 10 years and made contribution. You see that there are many places on the Earth, like for example in Brazil or India or China, where we have very few observations on the ground, and there we can make up somehow by using satellite observation. Next slide, please. So here you see the comparison of the bottom-up budget, which comes without using the atmospheric observation on the left, and on the right there is a figure that comes from adjusting those emissions by using atmospheric observation both globally and regionally. So regional patterns of atmospheric concentration are useful to adjust these emissions so that they match with atmospheric concentration time series. You see on the left there is a fossil fuel production and use. This 128 megaton means, or teragram I would say. The large part of that comes from natural gas leaks. It's about 80 teragram, and about 40 teragram comes from coal mining. The coal wells are ventilated and methane is emitted to atmosphere, and also open coal mining also produce methane. A larger part comes from agriculture. Agriculture is emissions from rice paddy fields, the animal, there is a waste emission at landfills. When we put organic matter into landfill, in an anaerobic condition without access to oxygen, the composition of organic matter happens in the anaerobic way, and it's producing methane instead of carbon dioxide. Also, we have biomass burning, which is mostly forest fire, but it's also the biomass burning that happens when people burn the waste and use fuel wood. A very big contribution to the emissions on our natural side is wetland emission. Wetlands are widespread both in a high latitude in Siberia, Canada, and tropical regions like Indonesia or Brazil, and they emit that close to 180 teragram methane globally. Very uncertain part is other sources which we consider less studied. For example, geological emissions from volcanoes, mud volcanoes, seeps. Are there very few places we can observe them, and we have uncertainty where there are other places, and then also the emission from minor sources. So if we compare the emissions that we take from the bottom up without using atmospheric observation, they are much larger than the ones that we constrain with atmospheric growth rate, and this gives you a difference between growth rate that you take with just bottom-up emission of about 100 ppb per year, and with observed emissions, observed concentration with about 13 ppb. So I think it's better to ask Prabir to continue.
Okay, thank you, Samil. So I will take you to little bit more detail in terms of the regional emissions. So here is a map. If you look at the methane emissions we know of from the globe and from different grids all over the world. So if you look at that, and then we can divide that things into few latitude bands, in this case tropics, the 30° north and the south of it, and 30 to 60° north, which is like mostly like America, Europe, and then China and the developing countries. And then there is a north of 60° north, which is kind of a cold regions. So in all these things, we have a separate interest, and then we want to understand them better. So if you want to look at this kind of aggregated emissions in these 3 latitude bands, you will see the tropical tropical and southern land is most emitting. Is a 64% coming out of this area, and then the temperate North America and temperate north latitudes, North Hemisphere latitude 32%, and then north of 60° north is about 4%. So what in general what you will see here is that these kind of numbers for how much methane is emitted from different parts of the globe are kind of proportional to the amount of the number of people living in those places. So it's very closely linked to our livelihood. As if you have seen, remember the source sectors we know of for methane. And if you look at the further decomposition of this total emissions into different source sectors like wetlands, biomass burning, and those and such and others. And then here that every panel there are 2 bars. The left one is top down, which means the inverse model results, and the right bar is bottom up, means the inventory based estimations. So generally we understand pretty well for the different sectors in all the latitude bands, but except the other emissions which we discussed, we also that we have much unknown in this, and the emission inventory based results and our top down, the atmospheric observation based estimations really do not comply at all in this area. So as you discussed already, that in these other sectors, 80% of about 200 teragram, about up to 190 teragram emissions is just coming from the fresh waters and geological. So freshwater emissions are estimated to be about 120 teragrams, and we need to understand this better in the future. So right now, I think I leave you here that this is the most uncertain emission sectors as we know of today from the bottom up and top down comparisons. And if you want to know further details of what has happened to the different emission sectors in the last 30-40 years, so you can plot the emission sectors with time, and it's a stacked plot. That means if you add all the emission sectors, we will reach the total amount of emissions which is going on at this moment, or something like that. It's about 600 teragrams globally. And I have shown here some of the numbers from 2004 to 2016, how this emission inventory have, or based on the top-down based estimations have changed over the time. So you can see that different emission inventories. And then one thing we want to highlight here, the fugitive, these are anthropogenic emissions from the coal mining and the oil and gas exploration. So these are the sectors where we have the emission from the supply chain. When you do the mining, when you do the gas leaks on the transport and etc. etc. It's not really the consumption side. It's mostly like supply chain side and the animal farming and say agriculture in general, manure management, etc. And so similarly, so the methane loss rates you also can calculate using atmospheric chemistry models, and we saw that how it's changed with time. So what you see here, the maximum of the about 90% of methane is lost by the OH chemistry, and we must understand. The point here is that we must understand this loss part, which is now done by the atmospheric modeling, in order to understand the budget, what is remaining in the atmosphere, which is the light, the bottom part of the blue color here, which means that the emissions, most of it is lost in the atmosphere, but only a small fraction, which is like a let's say 10-15 teragram per year out of 600 teragram is remaining in that atmosphere with some variability. So to understand that small fraction, we need to understand this loss and the emissions in total as you go along with time. So that's the point in this case. And then if you take you further down to regional scales, so it's like I am showing here the time series of methane emissions from 2 regions. One is the East Asia, we call it, China, Japan, and Korea, and the tropical land, which is like I showed you before, that latitude band in the tropics, 30 to 30 in the south, and then in the black line is the inventory-based estimations, and the blue line is the atmospheric inversion-based estimations. And if you try to understand this better, so you can see that the black line, if I see how much it has changed in the last 10-15 years, so you see that it's most of the emissions coming from the East Asia, and it's mostly dominated by the coal mining. On the other hand, it is slightly lower in terms of how much is emitted from the the kind of agriculture and the waste management. But if you go to the top-down balance in this case, like using the blue curves, so if you do this inverse modeling and then you can come up with a new estimation, so you see that the East Asian emissions seems to be lower than what we have in the prior estimations, like the bottom-up estimations, while the tropical emissions remains roughly same. So the balance changes depending on what we understand from the atmospheric point of view and what we understand from the inventory point of view. But these things are like a kind of exchanging information. We are improving things with time. And just to give you some numbers here, I showed this example. And then we are also looking at the various site-specific level. This is a research we have conducted in India. It's agricultural plots in the research institute called Indian Research Institute. And there we experiment with the different rice cultivation types. For example, in this case, conventional transplanting, which has been going on for thousands of years. And the system it's a new technique 30, 40, 50 years back, which has been promoted. And by doing this kind of changes in our rice agricultural practices, we can actually reduce methane emissions by up to 30-40%. And this is without reducing the yield in the rice, so which is very important for the farmers. But we can do this kind of changes smoothly in the transition for the rice practices in the reducing the greenhouse gases and also keeping the rice yield not lost. And we can also, like, that there are also other greenhouse gases which can come out from the farming. So in this case, N2O, we also account for that. And then we come up with the global, total greenhouse gas budget in terms of CO2 equivalent by adding all the emission. But even here, we see that there are certain reductions, very clear reductions in the emissions of the greenhouse gases from the rice cultivation when you switch from the conventional transplanting to rice system rice intensification. And these results have been produced and continue and communicated to the people around the country. And now I just try to summarize here that we have done. So there are uncertainties we have in terms of the, for example, the methane loss in the troposphere. So we can think about where the methane is lost, and we can think about how the methane is lost with time, the internal variability, and also the long-term trend. So these things are actually work in progress. We are making a lot of progress in these things, but I think we still do not have a very confident estimate to give, or we have not done too much in the GCP at the moment in this respect. So one thing also, we want to bring some sort of clarity in the bottom-up estimations. So we do not think that the bottom-up and top-down estimation for the other sectors should be so different. But then we also need to have a clarity between the emission sectors. For example, the fresh waters or the tree emissions or the wetland emissions, they all in the same locations. So we need to bring avoid double counting. We need to improve the clarity between what emissions are coming from what level and what locations. Then geological sources, there are very large range. And of course, we'll also discuss that we need more tracers, more kind of signals in the atmospheric methane to identify which kind of sources are changing and things like that. And then, of course, so this will also be discussed, top-down modeling, which improved. What I want to highlight in that at the end is that we need the policy developments where you can think about different aspects of methane and greenhouse gas cycles. In most cases, there are co-benefits. I gave you the rice paddy example, without reducing methane emissions, without yield compromising the yield. Similarly, the JICA, I think there's a lot of work in the West South Asia. For example, how to manage the waste, which is like lying all around the place, or maybe getting heaped up in some areas, how to process them and to clean the environment and also reduce methane emissions. So such things like a co-benefit, a lot of work can be done, and it helps everyone. And I will just leave you with a slide, which is like a highlight from the GCP budget. I think we will be running late, and we can take questions, or you can leave the question for the next discussions. Thank you.
Thank you, Shamil and Pabia. It's a very concise highlight. I'm sure we can discuss some of this more in the later session, right? As I see, we don't have the question at the moment, so if it's okay, let's move to the next speaker. Yep.
I suggest everyone to use chat to give us questions, so we'll look at chat. Thank you.
Thank you. That's a good idea. And please also, maybe introduce yourself and where you're from today. That would also give the panelists some ideas of, how we could address the question that you have, or, our talk better. Yep. So next talk, let's move to the measurement of methane by Tojima and Mashida-san. Yep. Please.
Okay, can you see my presentation?
Yep.
Okay, so I would like to start my presentation. I'm Yasunori Tojima from NIES. In this slot, I'd like to show NIES activity to observe atmospheric methane. And from me, I would like to show the surface observation. And after my presentation, Machida-san will present aircraft observations. And this is the content of my talk. Is first I would like to show the objective of the atmospheric methane observation and NIES observation network, and then I will show some result of each places, and finally I make concluding remarks. Okay, so why we observe the atmospheric methane? So in Shamil-san and Patra-san's presentation, we have now constrained the methane budget by using top-down approaches, but still there is some great uncertainty. So to better constrain the methane budget by using a top-down approach, we need to extend the methane observation network, especially to the sparsely observed regions such as tropical region, China, India, Siberia, Africa, and so on. So this is, okay, I'm sorry. So this map shows the observation network. And as you can see, there is some gap in the places there is not sparsely observed. And below, a bottom figure shows the satellite data. And the tropical region, there's some, we cannot measure the methane concentration because there is often cover the cloud. Okay, so this map shows the NIES measurement network, and the red circle is a place where the flask observation have been carried out, and blue squares represent the place where we conducted the in-site observation. In addition to this ground site, we also use a cargo ship sailing between Japan and North America, and Japan, New Zealand, and Australia, and Japan, Southeast Asia. And we collect their samples, which is shown in small red circles. And recently we have started the in-situ shipboard observation, and it is shown in the blue lines. Okay, so now we have very huge network in Asia Pacific region. Okay, so I showed some result. This is the atmospheric methane observation at Hateruma Island and Cape Ochishi. And this is a tower, and at the top of the tower, we have set the air intakes, and we observed in middle of 1990s. And blue is a Cape Ochishi, and the red is the Hateruma observed result. And there is show the clear seasonality and gradual increasing trend. So 6 line is a trend line, and the bottom figure show the growth rate. As you can see, the clearly show the gradual decreasing growth rate during this period, and then again increasing start in 2006 or 2007, and then the growth rate is accelerated in 2040. These data clearly show the background change in the Western Pacific region, and here I have no time to explain detail, but this data have the signals from the continental emissions. Okay, so next, Achida-san and Sasakawa-san built the observation tower network in Siberia, which is named as JR station, which means Japan, Russia, and something. And this right figures show the observed methane change, and there are clear seasonality and big change. And as you can see, there is some data gaps here. This gap means that it is very difficult to keep the observation, because this is a photo showing the site. It's a tower, but around the site, there is no shop, no home center. So it is very difficult to keep the observation. So this is one of the results. This is a smooth fit curve to the data in 3 Siberian sites, and the motifs show the background data. And usually the methane shows the minimum in summer and maximum in winter or early spring. But in case of Siberia, there is 2 peaks, and in summer, there we show the we can detect the big peak. This is derived from the emission from wetlands. So this is a model calculation, and so this Siberian data can constrain the biogenic emission from Siberian wetland in summer, and also the fossil fuel related emissions from Eurasia in winter. Okay, so next we move to the Southeast Asia observation. This is a case of Indonesia, and this is a figure shows the observation systems. As you can see, there is big, expensive instruments are set in this site, and this is a very rich project, and three sites, Serpong and Bogor and Sibe. I'm sorry, I can read. And these three sites, and the methane shows a very big diurnal change in Serpong, which is near the Jakarta. And from mountain site, the methane increase is reduced. And these data clearly show the emissions from the megacity of Jakarta. And also observation is also carried out in India and Bangladesh and China. This photo shows a sampling point, and in Nainital in India, this is a mountainous site, and Komila in Bangladesh, this is a lowland, and Guian in China, and these data show the very elevated methane concentration in comparison with the background site. So these data also constrain the emission from this site. And we also observe the methane concentration by using cargo ships. And this is the example of the observed between Japan and Australia. And this figure shows a time, latitude map of methane concentration. And the bottom figure is the growth rate. And this data clearly constrains the background change in the Western Pacific region. And in addition to this flask sampling, we also observe the methane concentration based on cavity ring down instrument on board. And so this is example of the observed in Southeast Asian region. And blue is background site, this line, and red dot represents observed in this region. And we, as you can see, the very high concentration is has been observed. So these data also constrain the emission from Southeast Asia. In addition to this concentration observation, we recently started the carbon C13 of methane measurement. This is an example of the methane concentration and carbon isotopic data. And so this, in association with the methane increase, the carbon isotope data shows the increase. This means a heavy source of isotopically heavy source is influence this observation. So this data is useful to partition the sources between the biogenic and the fossil fuel derived contributions. So finally, I conclude my talk. So NIES has huge amount of and unique methane data for Asia Pacific region. So our data will improve the top-down estimation. And we need to proceed the methane observation research in nature and sharing of the achievement with the international research communities. Thank you. Please, Machida-san.
Okay. Can you see? Okay. Thank you very much, Tojima-san. I will show the same kind of atmospheric observation by using aircraft. So this is the list of my contents. First, I will show NIES observation network for aircraft, and I will show the two topics. One is methane observation over Siberia, and second one is methane observation in UT areas. UT areas means upper troposphere and lower stratosphere region. and concluding remarks. So this map shows a NIES measurement network by aircraft, and blue circle shows the chartered aircraft observation at the 3 sites over Siberia. And the red color shows methane observation by commercial airliner by a controlled project. Both observations are carried out by sampling method. This picture shows the atmospheric methane observed over Surgut in West Siberia at 1 kilometer, 4 kilometer, and 7 kilometer altitude. As you can see, methane concentration shows secular increase, but the seasonal variation is not so clear in Western Siberia. But in over Yakutsk in East Siberia, we can see a very clear seasonal variation with minimum concentration in summer, and the peak-to-peak amplitude is larger in lower altitude compared to upper atmosphere. And we compromise average the seasonal variation of methane over Surgut, Novosibirsk, and Yakutsk. As I said, in Eastern Siberia, Yakutsk, we can see a very clear seasonal variation with minimum in summer season by the radical reduction in summer season. This is a very general compared to the coastal side. But in Western Siberia in Surgut, as Tojima-san already said, we observed a very huge amount of emission from wetland in summer season. This consists of second big peak in summer season. So the seasonal variation in wetland area is not so clear compared to the forest region in over Yakutsk. And Novosibirsk located in the intermediate with Surgut and Yakutsk. So anyways, this kind of seasonal variation shows the very clear influence from the surface condition of methane emission. And this figure shows the long-term trend of methane concentration over Surgut in West Siberia at 1 kilometer in red color and 5.5 kilometer at blue color. And interesting is the difference of methane concentration between two altitudes. It means the vertical gradient of methane in over Surgut, and the difference of concentration are decreased year by year in these 20 years. And we compare it by modeling result. By observation, the difference the difference between 2002 to 2006 and 2009 to 2013 is 9 ppb by observation. And we estimate the tact tracer model. By the tact tracer model, the contribution from Europe is 6 ppb within 9 ppb, but the contribution from West Siberia is only limited. So it means this kind of decrease in gradient is mainly due to the methane emission reduction in European region. Okay, I will talk to the second topics and the atmospheric observation in UT region. But generally, the tropopause height is lower in higher latitude compared to lower latitude. It means when we fly to the Arctic region, for example, between Japan and Paris, right, we across the Arctic region. So the tropopause height is lower in higher latitude. So it means even we fly in same altitude, we can sample not only from tropospheric air, but also in stratospheric air. So we can observe both tropospheric and stratospheric air. So this figure shows the time series of methane concentration in upper troposphere and lower stratosphere region. Red color shows the troposphere, and blue or purple color shows the stratosphere. So as I said before, the upper troposphere the seasonal variation is not so clear in troposphere, but in stratosphere we can see a very clear and very big amplitude of seasonal variation. This kind of large seasonality in lower stratosphere is due to one is in wintertime downward motion of air by Brewer-Thompson circulation makes a very steep decrease in methane concentration. But in the summer season, tropospheric air intrusion make a very steep increase. So this kind of on and off of air intrusion makes a very large seasonal variation of methane in lower troposphere. So it means when we measure the methane concentration by aircraft, we can understand the air transport by Brewer-Thompson circulation and tropospheric intrusion. The conclusion, one is aircraft measurement can get a large footprint. It means we can get a spatially representative data. Then we can get the average seasonal variation, and we got the information from the source contribution in Surgut, Novosibirsk, and Yakutsk. And second one is particle profile, give us a very good information to understand the surface fluxes, such as over Surgut. And third one is data from UTLS region, give us atmospheric dynamics information, such as Brewer-Thompson circulation and air exchange across the tropopause. And finally, I would say more dense observation of aircraft leads to better understanding of global methane cycles, such as emission information and transport information. That's all. Thank you very much.
Yes, sound is not clear, I think.
Sorry.
Good.
Okay, sorry about that. So thank you, Machida-san and Tojima-san, for the wonderful talk of how we measure both the methane from air and also inland observation. Right. So if you have any question, please put on. I see one from Anna. So at global perspective, I wonder if we are getting closer to producing methane emission data set at national scale. For example, emission number attribute to each country over the global, similar to the global carbon budget that GCP produce annually for CO2 emission. Thank you. What do you think? So Tojima-san and Machida-san, would you like to make any comment regarding to, are we getting any closer to kind of like, making, national evaluation on methane emission?
So from observation, it is difficult to estimate the methane emission because so we need some inversion study or something like that. And but now probably it is very difficult to a small country to estimate the emission from small countries. But if there is some bottom-up estimation and combining the transport model, we can check that the emission is correct or not by comparing with the observation. That's one way to check the emission inventory or something like that.
Thank you. Chamil, I see your mic on. Would you like to make any remark or comment?
I can add that there are countries that make emission estimate combining top-down and bottom-up. And most countries provide bottom-up estimate to UNFCCC. So there is some work ongoing in many countries to add atmospheric verification, but it will take time because establishing a network that is targeting national emission requires a lot of new expertise and big investments. So it is progressing rather slowly. But of course, in many countries, there is a determination to do that. And maybe in Japan also, there is a project on observing methane on a sky tree in Tokyo. So that will contribute to estimating Japanese methane budget better.
Thank you. Yeah. So we will come back to this topic again. So let me thank Tojima-san and Machida-san again for this. Yep. Thank you very much. We move on to the next topic. Now that we hear about measurement of methane, now it's about the modeling of methane emission. This talk will be given by Akito Ito-san. So let me, please go ahead. Thank you.
Thank you, Pirapan-san. Can you hear me? Can you see the screen? Okay.
Yes. Okay. Thank you.
My name is Akiko Ito, National Institute for Environmental Studies and JAMSTEC. I am working on some kind of bottom-up approach, especially the modeling of natural emission and wetland methane modeling. So my talk focuses on the natural emission and wetland modeling, just briefly. This is the content. First, I explain briefly about the estimation of wildfire, termite, and geological emissions. And then I focus on switch the focus to the wetland emission, estimated by modeling. What kind of model was used for the GCP census, and I show some results. This is a summary slide of GCP methane 2008 to 2017. You see the middle part, the natural sources of methane, including biomass and biofuel burning. Biofuel burning is anthropogenic, so the natural source is the wildfire biomass burning. And wetland is the biggest source of methane from natural sectors. And other natural emissions include various kinds of sources, such as inland waters, geological sources, oceans, termite, wild animals, permafrost, and vegetation. The latter sources are very minor, such as wild animal is only 2 teragram, and permafrost is only 1 teragram. But other inland waters and geological is very substantial. So we need to specify, investigate the distribution and temporal variation of the methane emission from natural sources with credibility. So this picture, this slide explains how to estimate the wildfire emissions. So we global carbon project census use 5 different biomass burning emission inventories, mainly based on remote sensing, such as MODIS. So first, the emission inventory estimates the distribution of burnt area and multiplied by the emission factors or the fossil fuel accumulation. This inventory estimates the distribution of wildfire emissions. So the bottom bar figures shows the comparison of the biomass burning emission by bottom-up approach and inverse estimation using the atmospheric data. So you see the wildfire explains about 70 teragram methane emission on average, and bioenergy, this is some house use of fuel biomass for cooking and heating explains about 20 teragram of methane. So the total is about 30 teragram of methane to the atmosphere by biomass burning. This is comparable with inverse estimation by using surface and COSAT data. And termite emission is very difficult to estimate because it is very local emission. But we estimate the thermite emission using a kind of empirical model shown on the left hand. So in this synthesis, we use some empirical model between the gross primary production. This is a vegetation photosynthetic productivity and termite biomass distribution. So uses this kind of exponential relationship between the two terms. So when the termite occurs more under the high productive vegetation. So by using some kind of emission factors, the specific to land use type, we estimate the termite emission globally. The total estimation is 10 teragram of methane per year, mainly from subtropical and tropical areas. This emission has little internal variability and seasonal variability, we guess. And geological sources includes was newly included based on the new dataset published last year by Giuseppe Icioppe. This dataset includes emission from mud volcano, seepage, something like that. So uses the global distribution of geological methane emission, as shown here. And we estimate the total emission is about 50 to 60 teragram or 40 to 60 teragram. This is quite substantial. So uses some strong source in also in Japan and other mountainous regions. So I focus on the wetland emission simulated by process-based models. The simulation protocol was developed by Benjamin Porter and Chen Zhang, Goddard Space Flight Center, NASA. In this protocol, we conduct 5 kind of simulations, but we use mainly use first simulation. This is a diagnostic simulation driven by CRU climate data. So the diagnostic means that we use the same wetland area maps. This is called WAD2M. This dataset includes swamps, the remote sensing inundation data. In this dataset, paddy field was removed by using Milcat 2000, and inland water was removed using GSW, different dataset. So by using this dataset, we conduct a simulation from 2018 to 2017. The temporal resolution was of output was monthly, and the spatial resolution was about half degree. This is about 50 kilometers. So you see the distribution of maximum wetland area on the left hand. This is a temporal change of inundation. That means the area with saturated soil water. So you see the high water inundation in West Siberia lowland, Hudson Bay lowland, and tropical areas such as Amazon, Congo, and Southeast Asia. So, but you see the very strong seasonal temporal change in the inundation area, as shown here. So we use this kind of data to drive the model. So in this synthesis, we use 13 models as listed here, including the model from Canada, United States, Europe, and China, and Japan. So we made a contribution by conducting a simulation data and supply the simulation output data. And it is very difficult to explain the model structure, but just briefly, the model has this kind of wetland schemes. In the scheme, we estimate methane production by microbes and methane transportation from wetland area to the atmosphere by diffusion, evolution, and plant transportation. But these processes are strongly dependent on environmental conditions, such as temperature and water table depth. So these models differ in the parameterization of these environmental conditions and biological processes. So this is an example of a result of methane emission simulated by my model. This is a result of visit model. So you see high methane emission from tropical wetland through the year round, and you see the very seasonal strong emission from boreal wetland, and you see some methane emission also from temperate wetland. So the picture included in the GCP synthesis published by Sanura is average of 13 models. You see the very strong methane emission from wetland in tropical regions, because the methane emission occurs through the year round in this region. And 13 models differ in the methane emission strengths a bit from the 100 teragram simulated by these models, TEM, OPD and TEM, and TEM and triple X GHG, and 180 teragram by JS Baha. And my model is about 160 teragram per year. So the small change was found between the 2 decades, between 2000 to 2009 and 2008 to 2017. So the temporal change or interannual variability was not so strong in simulated methane emission by the models. So this is a summary. Natural wetland account for 149. This is the average of 13 models, teragram methane per year. This is about 20% of total emission in this period, with a weak decadal trend. Wetland models were used in global bottom-up estimation driven by historical climate and inundation data, but there remains substantial uncertainty in the models and the data. So these natural sources, including permafrost, are sensitive to climate change. So we need more research to conduct a mitigation for society. Thank you.
Thank you very much, Ito-san. Yep. So we have some time, I think, for one question regarding particularly this emission modeling. So I saw some question in the chat box, but I think that can be addressed later in the overall panel. So is there any question related to emission modeling in particular? You wrote on your slide, permafrost is time bomb, question mark. Could you tell us a little bit more about that part?
Yeah, at present, permafrost is not so strong source. But in the future, when global warming proceed, the more severe global warming or temperature rise occurs in northern Arctic area. So more permafrost thawing will occur, then the more methane can be released to the atmosphere.
So kind of feedback, right?
Yeah, but we don't know when or how much will it occur. Yeah.
Thank you. And okay, we have 1 more minute, so I will ask another question. You said for natural wetland estimation, right? There's a lot of uncertainty. There are obviously like 13 model that to kind of like contributing to address this uncertainty. You know, what are the difference and how do they contribute to address this uncertainty?
Yeah, so we need more basic knowledge about the biogeochemical processes on the methane production and transportation. So we know little about environmental regulation or microbial processes on methane production. So we need more fundamental research to constrain the models. And also we need some kind of large-scale emission observational data for methane fluxes, and some isotopic measurement is also effective.
Thank you. So sounds like a lot of more challenges in that area, right?
Yeah.
Thank you. So we could come back to you again in the panel discussion, right? So if we move to the next speaker, Niwa-san, on the recent methane growth, right? So he will talk about the trends and what drive the methane growth in the recent year. Yep, over to you, Niwa-san. You're on mute, I think. Please unmute yourself.
Okay, can you hear me?
Yes.
Sorry. So good afternoon, everyone. My name is Yosuke from National Institute for Environmental Studies. Actually, my contribution to the GCP methane was from collaborative research with Meteorological Research Institute, MRI, which is my former affiliation. So first of all, I'd like to express my appreciation to the MRI colleagues. So in this presentation, I will talk about the result of the paper by Jackson et al., which is a side paper of GCP methane. The key point of this paper, I think, is that anthropogenic emission contributed the atmospheric methane growth in the recent decades. First of all, I will explain how the atmospheric methane is increasing in the recent decades, and then I will introduce the findings of GCP methane that Jackson et al. Focused on. And in the later part of my talk, I will touch on some future perspectives, especially of the top-down approaches.
Niwa-san, just before we go on, is your screen shared? We don't see your share screen at the moment. We don't see your presentation at the moment.
Really?
Could you press the share screen button if you intend to use the PowerPoint?
Okay. Let's see. Is it okay?
Not yet.
So
there is a green button at the middle, bottom part of the panel. Their screen.
Okay, can you see my slide?
No.
Okay, I will share your slide from my computer. Oh, is it okay now?
Is it okay?
Not yet.
Really? Oh, okay.
I got your slide, so hang on. If you continue,
it's the message saying the sharing viewing is failed.
I see. Okay, I will share your slide.
Okay, thank you.
Yeah. Okay, please continue. Thank you. So.
Okay, so the please press button. Yeah, and please go to the next slide, please. Okay, thank you. As you may know, we have three major greenhouse gases: CO2, methane, and N2O. And in the among three major greenhouse gases, methane has the most largest increase rate compared to the level of pre-industrial level. which amount 257% in 2017. And another point the methane has is that methane has the most variety of human-induced emissions, like fossil fuel, oil and gas, and also from agriculture and waste cultivation. And this is another key point of methane. Next slide, please. Okay. This figure shows the growth global total of three major greenhouse gases, and in these figures, you may easily see that the methane has very different growth feature compared to the other greenhouse gases. We can see from 2000 to 2006, the methane atmospheric growth is stagnated, and after 2006 or 7, the stagnation is stopped, and the methane atmospheric methane level is again increased. And this figure shows so this time GCP methane is well covered both two periods, the stagnation period and the increasing period. And the former one, which was published in 2016, is focusing on the period from 2000 to 2012. So this time it's more better to cover this increasing growth feature. Next slide, please. So before going to the budget, going to the causes of the increasing trend, we would like to talk about the budget itself. So there are already explained by many speakers the top emissions and the things. There are many delicate balance between the sources and the sinks. The sink is mainly contributed by chemical reaction with OH, and which amount about 600 teragram. And the emission has a comparable to or a little bit larger amount, which is amount from 600 to 700 teragram per year. So there is a very delicate balance between the source and the sinks, and the imbalance about 100 teragram contribute the recent methane growth. Next slide, please. So here I'd like to say that this invergent top-down approach studies performed in the GCP methane assume that decreasing of OH is not probable. However, of course, it has significant uncertainties, and this topic is very controversial, but please keep in mind this assumption. Next slide, please. So the side paper, Jackson et al., was published from Environmental Research Letters this year, and it's focusing on the recent grade from the stagnation period to 2017. During this period, atmospheric methane has increased by 80 ppb. Next, please. And also this figure already shown by previous speakers, and this figure shows the where and how much emission methane was emitted to the atmosphere. So we can see that a large amount of emission were released into the atmosphere from tropics and the southern hemisphere, and also northern mid latitudes, and we found very small amount of emission in the Arctic regions. And it is interesting to note that anthropogenic emission is dominated in the mid-northern latitudes. So fossil fuel and agriculture is dominant sector in the northern mid-latitude. On the other hand, in the tropics and in the southern hemisphere, anthropogenic emission and also wetland and other sources, so natural emissions are comparable to each other. Next slide, please. So this figure shows the breakdown of emission estimate by region, and this figure also showing both top-down estimate and bottom-up estimate. So first, so positive value means the increase, contribute to the increase of atmospheric methane in the last decade. So first, we can see that anthropogenic emission from fossil fuel, which is brown color, and also agricultural emission, which is in bluish color, dominant to the increase of methane emission. And we cannot see any significant increase in natural emissions. And when looking at by region, we can see anthropogenic emission, fossil fuel emission from China, and Africa and the Middle East fossil fuel, and also agriculture emission, and also rest of Asia emissions are contributing the increase of methane growth. And also in the North America, anthropogenic emission is contributing, and especially this is dominated by fossil fuel emission use, fossil fuel emission in USA. Next, okay, sorry, go back to the, okay. And one more interesting result is that we cannot see evidence to date for increasing methane release from the Arctic. Thank you. Next slide, please. So go more to see more finer scale emission increase patterns. Here I show result from my inversion, which is derived from Nicomtium four-level system. The left top panel shows the difference between the mean flux of 2017 to that for the stagnation period, and the reddish color shows the increase, and the bluish color shows the decreased emissions. And as I said, Asian countries anthropogenic emission were increased, and from this figure we can see that northeast part of China and also South Asia, the emissions are increased. However, please press button, please. Could you press? Okay, thank you. So, however, in these areas, we do not have so sufficient observations. Actually, the right panel figure shows the locations of observations I used in that inversion, but in these areas, we do not have so dense observation network compared to the North America or Europe. Next slide, please. So to better constrain Asian emissions, we, a Japanese institute, conducting aircraft observations. The one is JMA aircraft, and the other one is Contrail commercial aircraft. which is already introduced by Majida-san. So these observations were performed in the upper troposphere. So you may think that the surface flux signals cannot reach so high upper troposphere, but they can do capture flux signals. So please press button, please. Yeah, thank you. So this is a simulation from the posterior flux of my inversion. So this is the simulation for September, which is when Indian summer monsoon is activated. So we can see a very high concentration of methane is uplifted over the continent and transported to the Western Pacific. So the flight route is here. So we can expect that these aircraft observations can capture this high concentration event and constrain Asian flux estimate. So thank you. Next slide, please. So here I want to touch on another limitation of inverse analysis. So as maybe discussed in the morning, I remember. So the inverse analysis top-down approach cannot exactly distinguish different sources because we are using only methane concentration data. So when the anthropogenic different emissions coexisting in the same place or the same time, we cannot perfectly distinguish those emission categories. So the right figure shows the anthropogenic and the wetland emissions we used, and North America has very complicated and mixed emissions. So in this area, we cannot maybe clearly distinguish the emissions so far. And the left figure shows the posterior error correlation, which is calculated from my inverse system. And this is showing that anti-correlation among the different emission categories for the global total. That we can see that very significant anti-correlation number is existing between wetland and the anthropogenic emission. So even for the global total, the top-down approach might be not be able to distinguish the emission sectors. So this is one more limitation of our inverse analysis. So next slide, please. So to overcome this limitation, we are in near future we want to use isotope data. Isotope data have some information about different emission categories. The left panel shows the increasing of methane concentration and also decreasing trend of delta C13 of methane. So isotopes have very useful information to know to distinguish different emission categories. And using these isotope data, we have to harmonize the data set from different laboratories. So Umeda-san, he is my colleague of NIES, is now working on the synthesis harmonization of the methane isotope data. So this kind of work is very critical for our inverse analysis. So next slide, please. And finally, I'd like to note that Arctic. So I said no evidence to date for increased methane release from the Arctic, but there are many permafrosts, and actually this year we had very high temperatures in Siberia. So this kind of high temperatures could enhance, accelerate the melting on permafrost, and could a large amount of methane could be released from this kind of phenomena. So we have to keep attention to the Arctic as well. So next slide, please. So this is a summary, and the key point is for the recent decade, the atmospheric methane is increasing, and this is contributed by the increase of anthropogenic emission. And so please show up every comment. So please press button many times. Thank you. So there are the delicate balance between emission effect and after stagnation of 2000 to 2006, atmospheric methane has begun to increase again. And GCP methane has found that the anthropogenic emissions of Asia, Africa, Middle East largely contributed to the methane growth. So this kind of information would be helpful to our communities. And also fossil fuel emission in USA also dominate the increase in North America. And some future perspectives, we are now conducting Japanese observations, and actually I'm using these data to constrain Asian fact estimates. So this is ongoing work. And also in near future, I'd like to use isotope data to better distinguish different emission sectors. That's all. Thank you.
Thank you very much, Niwa-san. Yep. So, yeah, is there any question regarding the topic he addresses now, the recent methane growth? Please feel free to type into the chat box or Q&A. Yep. So, I think to kick start off, the current methane budget we compare to the pre-historical estimation, right? There's the question that come in is that how did we estimate the pre-industrial estimation?
So pre-industrial level is measured by ice cores in so Arctic and Antarctic regions. So in Japan, so Tohoku University are measuring the pre-industrial level methane concentration by analyzing ice cores.
Thank you. Yeah. So it's quite clear that the anthropogenic activity is the driving force behind the methane emission growth, right, in the recent year. You also, in your research, you also in your presentation, you also mentioned that there's regional differences between different methane emission and also of which sector is coming from, right? Like the tropical area is more, there's also a contribution from the nature as well. If we link that to the previous question from Anna, previously that she mentioned how do you think that, obviously in order to make each country responsible for their methane emission, we have to somehow accounting them at the national level, right? But at this moment, you mentioned in your talk, the challenges between the top down and the bottom up. In that, for example, the top down, there's a difficulty in distinguish the source of emission. Yeah, how do you feel like, or how do you see this challenge being addressed? Can we actually move toward having a methane accountability at the national level?
National level is very tough. It would be tough work for our inverse modelers. So maybe we have to use a very fine scale model, not only global, but also maybe using regional model is better to simulate methane concentration at very small scale. And also national level, we have to more dense network of observations to separate the spatial differences. We have to more very dense network, and so in national scale. So we have many challenges, and we have to many work on modeling and also observation.
Thank you. Yeah, to add to that, we also have a question like, how are the uncertainty in the chemistry transport models that lead to the error bars in the regional emission changes?
Yeah, so it only using a single model, it is very difficult to quantify the uncertainty of atmospheric transport. But so especially in GCP, we have very many models. So they are very different transport features. So using this model ensemble, we can somehow quantify transport uncertainty. So such kind of intercomparison of transport model is a key point to quantify uncertainties for atmospheric transport.
Thank you. Yeah, I like that word very much. The model ensemble is like, every different model bringing in together to contribute to ensure we address the uncertainty, right? Any other question or remark from other speaker? Please feel free to chip in. Okay, there's one from Masao Ichi. Is the current observing network enough to capture the large methane emission from Arctic in case it happens?
I think it is not enough. So in my the analysis of my inversion for GCP methane, actually don't have include Siberian observations Machida-san showed, but I'm already working on including the Siberian data, but still it is not enough to constrain everywhere in the Arctic regions. So maybe we have to expand hopefully we can expand the observation network in Arctic region, especially for Eurasia is very sparse even now. In North America, Canada are working very hard to expand the network, but in Eurasia we do not have still enough not enough observation. So
thank you. Yep. So Niwa-san will not come back to join our panel discussion. So let me thank you at this on behalf of the attendants and everyone to for your presentation today. Thank you very much. Yep.
Bye-bye.
Right. So next we move on to Naveen Chandra, who will share with us his method in budget assessment, his work on budget assessment by inversion modeling. Over to you, Naveen.
Okay. Thank you. Are you able to see my screen?
Yeah, that's good.
Is it okay?
Yep.
Okay, thank you. So thank you very much. So good afternoon to all of you. So today I'm going to speak on the synthesis of methane inversion using the top-down and the mostly at the top-down approaches. So broadly, I will cover two topics. One is the how much is the methane emission is coming from the globally and from the regionally and the regional contribution. And secondly, I will talk about the methane changes in the past decade, how the methane is going regionally changing and the globally changing, as well as the which sources are contributing on those kind of changes. So the introduction already given by previous speakers. So I will not go in the detail, but just I want to show that the methane in the atmosphere is currently increasing at a very faster rate in the past as compared to the past. So so to understand such kind of variation of methane in the atmosphere, we need to track the potential region where the emissions are changing much, and what are the dominating factors which are responsible for such kind of changes in the atmosphere. So this kind of assessment will be helpful to construct the mitigation policy for the climate change. So GCP methane synthesized all the current knowledge of global methane budget based on the different approaches, different data and tools. So briefly, there are two approaches. One is the bottom-up approach, which include the emission inventory from the different sources like the anthropogenic emissions from the edgeguard gains and fire emissions from the GFAD and other biofuel estimates. And there are other things also, but there are the biogeochemistry models already discussed by the Ito-san, which is used to simulate the methane emission from the wetland and the other rice and other sources, termites also. So another one is a top-down approach. Top-down approach is use all these information in the transport model using with the help of observations across the globe. It helps to refine the bottom-up emissions to give the more correct estimate of emissions globally and the regionally. So this is a very brief schematic for the inverse modeling. So inverse modeling is a tool to estimate the causes. Causes are the sources, different sources which are at the surface. Already we have discussed based on the consequences. Consequence is the atmospheric changes in the concentration. So how we estimate the fluxes in the inverse model. So we have the flux map from the different inventory. Then we use we make a priori fluxes using those available inventory data and the data-driven data. And then we run our transport model, which will give the concentration of methane at every grid, depend on the resolution of the model. And then we have the observation across the globe, and then we try to optimize the observation and the simulation from the transport model, and then this will help to correct the input emission. We call it the a posteriori fluxes, that is the top-down fluxes, also the top-down fluxes, and it will give the emissions at each grid of the globe. So as you can see that already discussed by the Tojino-san and the Matsuda-san also, there are the very limited data network, especially over the Asia region, and then to fill this gap, satellite data also can be used in the observation to optimize the fluxes. So but they have the different kind of challenges. I will not go in the deep of what are the challenges between observations from the in-situ and the Gaussian data. And in the GCP model, there were the 9 models used in the GCP synthesis for the inverse analysis. So there are the red colors. So those models are also participated in the past GCP synthesis in 2016. And there are 3 additional models in this synthesis GCP methane to 2020. So there are total 9 models have participated in the inverse analysis. So now I will come to the global budget. So this is the global budget for the recent decades, from 2008 to 2017. So we can see that these are the average for all models, inverse models given in the numbers. And these are the inside the bracket. They are the range, minimum or maximum range. And these are the number for bottom-up emissions and the top-down emissions. So bottom-up emissions are almost 30% larger than the top-down emissions, because as we see in the previous talk, there are the large natural sources in the existed in the bottom-up emission. That's why there are the very large emissions from the bottom-up estimation as compared to the top-down estimation. And if we come to the sources, which sources are how much emissions are coming or from the which sources, then there are this figure shows the emissions for this period 2008 to 2017, the average emissions. And this is the range. So the range is due to the different models. So these are the average emissions, and this range will show the range due to the different models. So if we exclude the natural things, if we see the relative contributions from the bottom up emission, we can see that the very high contribution bottom up suggests also the very high contribution from the agriculture and wasteland, and it comes from the wetlands, then the fossil fuels, and then the biomass burning. So, and if we see the top-down estimate, also the relative contributions are same, although there is a difference in the average emission. So, relative contribution in the sense that is still agriculture and waste contribute very high, and then the wetland emissions, and then the fossil fuel emissions, and biomass. If we see only these things. And so if we see that both the top down and bottom up are very close for both estimate for the agriculture and waste emission, but there are the very large gaps for the fossil fuel emissions, because if we see when we in the next slides, we will show that this is due to the fossil fuel large fossil fuel emission from the China region and Southeast. So if we now to understand the regional contribution in the total global methane emissions, so this slide shows the partition of the regions between 19 continental sites, and then this plot shows the total emission from bottom up and top down approaches. Bottom up and top down approaches for the average for this period. So here we can see that regionally also there is a large discrepancy between the top down and bottom up estimate. If we see that the China here bottom up estimate suggests that the China is the larger contributor in the global methane emissions, but when after the top down correction, it suggests that the Brazil is the larger contributor than China in the total methane emissions. And if we see that the changes in the top down and bottom up emission, we can see that there are 3 regions where we see the maximum change. One is the China region, where we see that the top down emission suggests that the low emission than the bottom up approach. Sorry. Equatorial Africa, the top down suggests the higher than the bottom up approach, and Brazil also same thing. So if you see the larger emitting region in the in the globe. So we can see that the Brazil, Southeast Asia, China, South Asia, Equatorial Africa, and USA almost accounted for the 50% of total global emissions. And this is the these are the total global emissions from these 19 regions. We can see that. After looking at the total global emission, now we will discuss about the change, how the methane emissions are changing with time in the past two decades. So these are the anomaly is plotted in this plotted from the different models. So these are the surface inversion and these are the satellite-based inversion. So almost we have so almost consistent global all models shows the consistent pattern in the emission trend in the past 2 decades. So, and there we can see that the largest emission changes occur in the 2006-7 and the 2013-15, and there are the consistency between the surface inversion and the satellite-based inversion is less than 5 teragrams, so it is quite consistent. So now, after we will discuss which regions are contributing in the global increase, global emission change in past 2 decades. So the emissions are, the anomaly is plotted for the three broad regions. So you can see that tropical region and the mid-latitude region contribute in the this kind of global anomaly in the past 2 decades. However, the boreal, so there are the boreal zones where we find no significant trend. So the boreal regions are already discussed in the previous by NIES, and that there are the lot of permafrost which are expected to release methane due to the warming, due to the air surface temperature warming. But we have not seen any such kind of increase in the boreal region. However, in the past, there can be increase can be seen in the boreal region because due to the positive climate feedback. So it means when more temperature, temperature will increase, then the boreal permafrost will increase more greenhouse gases, and if more greenhouse gases, again the temperature will increase. So there will be kind of positive feedback. But that is still not have seen in the past 2 decades. And these are the two different, and these are the change in emissions by 2 different by anthropogenic sources and the natural sources. So we can see that the anthropogenic, so the black line is the trend from the bottom up emissions, and this is the range from anthropogenic sources from the top-down system. So we can see that although there are the change in magnitude, but the trend is almost similar in the anthropogenic and the natural sources. So both top-down and bottom-up trends are quite consistent. So now we will discuss how global total methane emissions is changed in the past from 2000 in between the period of 2002 to 2006 and the 2013 and 2017. So this is the difference between these 2 periods, and this is the top down and this is the bottom up estimate. So we can see that almost 41 teragram have increased in the global emission. So the increase is mostly contributed from the tropical region, and also which is followed by the mid latitude region. And then if we see the regional contributions in the global increase, we can see that South and East Asia, that is China, is the most significant contributor in that global increase of methane emissions, and then the Africa, and then which is followed by the Africa, Middle East, and then other part of region. So here I also want to point out that in previous slide I have discussed that the Brazil is the largest methane emission hotspot, but the region which is contributing in the increase in past 2 decades, that is the South and East Asia. So this kind of these are different. So largest hotspot and the contributor are the different regions. So only so then if we see which emission sources are changing with most. So these are also the difference between the emission for these 2 periods, which is discussed in the previous slide. So here we can see that the fossil fuel. So the bottom-up approach suggests that the fossil fuel emissions are the largest dominating sources in the global increase. However, the top-down approach suggested that both fossil fuel and agriculture and waste are the equally dominating in the global increase in past 2 decades, for this period. So here again we can see that in the previously I discussed that the agriculture and waste is the highest contributor, and that the wetland is the second highest contributing in the total global emission. But the changes are occurring by the fossil fuel and the agriculture and waste emissions in the past 2 decades. So wetland emissions are almost not much contribution as have seen by the wetland emission by top-down approach. And now we use our Miroc ACTM model, which was also a part of the GCP for seeing the changes in the past 2 decades. So this red line is the Miroc ACTM run for the past 3 decades. And this is the GCP emissions for this average for the all inverse model, and this spread is the intermodal differences. So here we can see that all trends are quite our Miroc ACTM trend are quite consistent. So we can see that how the emissions are changing in the past also. Here we can see that the European emissions, European emissions are continuously decreasing since 1990 also. But the Russian emissions are also first decreasing now. Now the emissions are almost stagnant, and then start increasing, little bit increasing again, mostly due to the fossil fuel emissions. West Asia also they are the fossil fuel emissions. So in the Europe there was the agricultural emissions and the fossil fuel emissions consistently decreasing in the past 3 decades. In the East Asia, where we see that the very big increase from the East Asia, that is mostly due to the fossil fuel emissions, mainly from the coal mining, and the South Asia emissions mostly coming from the West and agriculture, agriculture. Similarly, Southeast Asia also. The Brazil emissions are also increasing, quietly increasing due to the agricultural emissions. And now the temperate North America emissions are also started increasing, particularly after 2004-05. So due to the fossil fuel emissions. So this kind of understanding is very necessary to identify how the emissions are changing with the time, and what are the potential where the emissions are changing most. And that such kind of information is very necessary to understand and to construct the mitigation of the methane emissions in the atmosphere. So this is the final conclusion. So we have seen that there are large discrepancy between the top-down and bottom-up approach in the globally and regionally also. And we have seen that the Brazil, there are the five most dominating regions which are contributing more than 50% in the global methane emissions are the Brazil, South Asia, China, South Southeast, South Asia, Equatorial Africa, and USA. And global methane emission, we have discussed that it has increased by 41 teragram in the period of past decades. And we have seen that the anthropogenic sources are mostly responsible for the rise in global methane emission, equally from the agriculture and fossil fuel sources. And we have also seen that the largest contribution in the total emission and the contribution in the global increase are different. So wetlands, although wetlands are the second largest contributor in the total global methane emission, however, not so significant in the increase in past 2 decades. So tropical regions play the most significant role as a contributor in the rise in global methane emission. So this kind of assessment highlights the major emission sector and dominant region for the climate change mitigation. So thank you.
Thank you, Naveen. Yeah, you shared very, light on the very complex topic in the inversion model. Particularly, what strikes me most is the slide number 6 that you have. When you compare the top-down and bottom-up. Could you, maybe delve a little bit more into that?
This one?
This difference, yeah. The 30% difference between the bottom-up and top-down.
Yes.
Yeah. Could you, basically the discrepancy you mentioned a little bit about, about this. But the implication, what is it like? This big difference when it's. I mean, for me as a non-expert in the field of inversion modeling, and also me, seeing this big difference is kind of like it's raising an eyebrow, isn't it?
So as we discussed, as Ito-san also discussed in the previous talk, there are the very large emissions from the fresh waters in the which are recently included in the bottom emission. We can see that those emissions in the other natural part. So this kind of large emissions are causing the high bottom-up estimates.
Mm-hmm. Okay, thank you. So could I invite other speaker to join me on the panel? We'll move on to the panel discussion. Now we have about 25 minutes or so. So please switch on your camera if that's all right. Yep, thank you. Yes, so today we discuss, we hear several presenters present their work on the methane budget, which is very much kind of expertise and very specific topic, right? So in this panel discussion, perhaps let's bring that back from let's bring it back to the kind of the entry point that we have, which is about the methane budget itself, right? So I will go to Prabir and also to Shamil. If you could maybe, share with us, what are, compared to the last methane budget, which was done in 2016, right? What are the improvement and progress that we have made, compared to that last release?
So I start.
Yes.
Yeah. I think one of the measures, the progress, I think, in my opinion, is that we are able to understand the budget itself, but then you are also identifying the places where you need to have improvements in our understanding as a community. Because one thing I was trying to show that the time series of the loss and then the emissions. So both the big amount, like a 600 teragram and 600 teragram there, are basically making the budget. And we have a very small margin of 10 to 20 teragrams, which are actually remaining in the atmosphere every year. And so that, I mean, one of the things that we really understand, we need to understand that how much is the loss. Then we can talk about how much is the budget, how much is the emissions to match the atmospheric constraint. So then that also goes back to your question in the last slide. And we have been discussing that there are a lot of emissions from the fresh waters, which you do not account in the top-down models. And why you don't account in the top-down model is that we do not have a global map of the freshwater emissions in some sense. That is already proven. So when you talk about like what the emission sectors which taken into the inverse model and are not taken into the inverse model are the kind of confidence we have in the bottom-up estimations. That's what I would say as an atmospheric scientist, that we do not know enough the freshwater emissions that we can put in our inverse models. Same thing we can say that for the tree emissions. There are propositions that the tree are emitting about 40 teragrams of methane every year to the atmosphere. But these trees are also overlapping with the wetland areas. So there are like overlaps and things like that, and which we do not know exactly like how to put in the models and how we validate or invalidate the emissions. I think one of the progress we are also making in this sense that we understand that there are options, but then also the atmospheric model is that we have a constraint on the OH loss. That is coming from the independent tracer methyl chloroform in this case. So if that atmospheric loss part, the OH concentration part, is changed, for example, if you can increase OH, you can bring in more bottom-up emissions into our inverse models. So these are the knowledge gap right now we identify, and that's what I think is one of the major progress we have made to identify exactly what are the knowledge gaps and how you move from here. I think I will stop there with that at the moment.
Thank you. Yeah, Shamil, yes.
Yeah, I agree with Prabir that we should fix many parts, and both globally and locally, and especially where the uncertainty are like inland waters. We need to propagate the in-situ observation research to modeling community a bit more faster than we do at the moment. The same thing applies to wetland mapping. The improvement in wetland mapping is still slow because the heterogeneity of wetlands is still not resolved in the remote sensing map having global coverage. And that input is lacking because without that, the modelers will have difficulty. Everywhere they will have to deal with the same type of wetland, just wetland, while the wetland ecosystems are quite different. It could be that the spatial scale varies from few meters, and the observation exists on all these small kind of ecosystem subtypes, but propagating that to global models is still difficult. So there is a lot of space for improvement of both measurements, the modeling, and inventories. The inventories that we have, like EDGAR, are based on it, like default emission factors, very limited spatial information, and they have a lot of space for improvement we have. But the progress is going on, and I'm quite sure there will be a lot of improvements by next budget in 4 years from now, for example. But we have to make effort to make it happen.
Thank you. That's a very good remark. Yeah. So one question for Ito-san, yep, from Inubushi-san.
Yeah.
So you read that. Thank you for
Yeah.
nice presentation. I have question about wetland emission model. How include quality of soil sediment such as peat or mineral and its depth, and how about effect of ENSO? Yeah.
Thank you, Inubushi-sensei, for these questions. The parameterization of soils is different between models, but many models doesn't consider the quality of soils because we have no enough data for the quality of soils. So in my case, in my model, I assume the uniform histosol in peatland and wetland. And I guess other models use similar approach, but if we have data on some kind of histosol quality or some soil quality data, we can separate the soil condition between the wetlands. So this is the next improvement of the wetland models, I think. But we already consider the difference in vegetation on wetland, such as the bog, fen, and swamp and marsh. But it's not so sophisticated approach to consider the difference in wetland. As to the second question, of course, we consider the impact of ENSO through the change in temperature and precipitation, because the drought caused by ENSO decrease the water table depth, then the reduce the methane emission in some case. But in several areas, ENSO also affects the biomass burning. So biomass burning also releases the methane to the atmosphere. So the ENSO has different impacts on methane emission by wetland and biomass burning. So the stories are a bit complicated. Thank you.
Thank you. Next question, I would like to go to the question from Kawamiya-san. Agriculture emission of methane is directly linked with food production, which brings a different kind of difficulty for methane mitigation. Compared to that of carbon dioxide, in what way would scientific achievement of methane budget be able to contribute to solve the problem of maintaining the balance between food production and methane mitigation? I think this question also linked to Anna's question, which is based on current scientific knowledge that is seem feasible for research community to propose certain action to reduce methane emission from anthropogenic source. So yeah, let's address these two questions together. Anyone would like to start?
Perhaps may I try? Or Professor may help us in the viewpoint of IPCC work, because for me, this kind of methane budget, this is a really scientific work, group work of top scientists, and this is a clear message for the basic data. And then this kind of data set will be compared to a kind of another synthetic work like IPCC. It has a working group 1, 2, 3. One is understanding the current situation. A second working group 2 may work for the estimate impact analysis, and working group 3 will bring more message to science directly. So I think this is a long way to go, and we are working in the very beginning, the starting point. But it is a kind of continuous work. So we're working now at this point. If you speak about this methane budget, this is the very beginning point. But this kind of data, without this kind of solid data, dissemination to the public will be quite much more uncertainty they have. So we have to go step by step to reduce uncertainty and make more clear result. We have to convey to the next step of work. And I would like to ask Fabius some advice.
Yeah, so
point of
I tried to reply Anna online. So I just replied to her comment slightly. And also, yes, it is linked to that, what Kamiya-san was asking. I don't think that the food is so interlinked with methane and the way we want it right now. So of course, the controlling the emissions from the animal inside the enteric fermentation, the ruminant itself, that may be tricky. But I think that also there are a lot of research going on the how we can prepare the feed for the cows, which can reduce methane emission a lot. So that is a bit complicated. Maybe it will take some time, but then some of the things for methane emissions are very, very simple. Like for example, the rice field cultivations. Indonesia also can throw a lot of light on that. He has done a lot of work. We have done together also what I was trying to show in one of the slides, that we can actually reduce methane emission from the rice fields without compromising anything on the yield. And you also need less water to the field, which means that you can save money on the irrigation. You can not reduce yield, but you can reduce methane emissions. It's just a concept. It's just a practice we have to change in people's mind. And the second thing I would just try to answer also is that pick up on that, the waste management. I think it's a very big sector, the waste management sector and the manure sector. There's nothing to lose at all. But of course, it needs some investment to implement that, how we collect garbage and recycle garbage and process garbage. So there are some investment is needed. So for example, JICA is doing a lot of work in South Asia. I was trying to scan their website and the activity they do in India, Bangladesh to process such things. I mean, they are like a kind of just need a goodwill and very small investment compared to what you have to make for CO2 emission reductions. The investments are very small, but I think the benefits are quite large. I would think the methane is a very low-hanging fruit for the emission reductions, and we need to convince ourselves. Yeah.
Thank you. Any other speaker would like to add on to this point regarding mitigation of methane? Yeah. If not, you'd like to shift the gear a little bit. So this question is to Machida and Tojima-san. Is, in your talk you talk about the land observation and also air observation, right? Which is involving a large network of stakeholders, both in the public and private sector, right? To kind of making this measurement of emission. What are the challenges in collecting these results and making sure that there's an ongoing, continuing effort to collect these results?
What do you mean?
Yeah, because in your talk, right, you mentioned about the network of both the air observation and also land observation that you bring the data into collection. So obviously, from my understanding, that is involving different stakeholders to making sure that these observations are being made on the ground and in the air. I just want to hear from both of you, like, what are the challenges in making this effort in data collection?
Yes, our observation is supported by many groups. For example, for continue the cargo ship observation, the ship owner can help a lot of effort. So to continue the observation now it's very difficult. So, but anyway, the observation is very important as a base of the, for example, the inversion study. So, yeah, we continue to effort. Yeah.
Thank you.
Okay.
Yeah. Hi.
Yeah. So the extent of the observation is crucial and very important. And also, as Tojima-san said, so our resource is limited. So collaboration with other countries, other scientists are very, very important. And we should make efficient collaboration and make efficient dataset is very important, I think. And also, another point of view, as for the data use, so we use mainly the scientific purpose, and also you want to use it for the results for the policy maker. And also, I think it is also important to show our data to ordinary people in the public, to show the real increasing of the greenhouse gases. Such kind of impact is very important to make an action to reduce the emission and something.
Thank you. That's very good point, Machida-san. Maybe I go to Jill's next about the involvement with the, how do we get the data out there and, to engage with the public at large?
Yeah, thank you. And I think this completely follows in line with some of the previous answers as well. Like, step one, of course, is to recognize that there is a large emission of methane and it's coming from various sources. And starting with the measurement gives us a an indication of what is out there and what the implications are. And then the next step is bringing that to societal stakeholders, to governments, to corporations, to individuals that are utilizing certain technologies or methods that are part of the reason why our behavior is causing methane emissions. Of course, there's a big portion of that that is natural, but there's also a big portion of that that comes through our individual decision making or even collective decision making. Bringing this knowledge out there, and I think this exact event is a very good example of the potential of that. Bringing that to these individuals that can gradually adjust their methods and technologies to decouple also if there is concerns of changes in or the necessity around changes in food production techniques, for example. Decoupling that with methane emissions is, I think, the ideal step forward. But for that, you need a mechanism. So linking the science to decision makers and to practitioners from various sectors.
Indeed, I think to catch that low-hanging fruit, right? I think we need to kind of. There's one specific question to Niwa-san, who is not here. He said Niwa-san pointed out the difficulty of separation of the emission source in the top-down approach. In the sheet 6 of Chandra-san, please let us know how to estimate emission source apportionment and its uncertainty. Navin-san, would you be able to address this question?
Okay, so here in the GCP, so it is a broadly we separate the sector information from the total emissions from top-down emission using the factors. So in the priori emissions, we know the proportion of different sources in the total emission. Suppose like 40% from wetland or something like that. This kind of proportion we know, and then we use same proportion factor in the for the total emission from top down inversion. So this and we assume that the emissions are changing at the same proportion in the top down inversion also. So we use those kind of factors in the total top down emissions to separate the different emission factors. So this may hold a lot of uncertainty because we are assuming we have some kind of assumption in this approach that the relative contribution is not changing with the time also. So this kind of assumption can make the uncertainty, but this is the very broad way to separate the sectors from the top-down inversion total estimates. But another way there are some models also which can optimize different sectors separately in the top-down inversion, but not all models are doing so.
Thank you. Yeah, if there's any follow-up question, please feel free to contact everyone in the panel. Yes, Shamil, please go ahead.
I'd like to add about the Niwa-san's question about separating anthropogenic and natural sources. I think the good way to do that is to add more observation close to the sources, more observation sites on wetlands, which is less influenced by anthropogenic, and more observation site near anthropogenic sources, which is often very far from wetlands. So local emission will give a strong local signal that can be used in atmospheric models for separation. That also from this result, I think is a very good input to observation planning, as that from GCP methane budget, we understand the importance of anthropogenic emission change. That we should look at the anthropogenic emission trends, and both in like energy sector, like fossil and agriculture, and I think through observation program is a good chance to use this output to advise agencies to increase observation of methane the kind of places where anthropogenic emissions are strong.
Talking about the final question, actually, about projection of methane budget, right? Do we have any work ongoing on the projection of the methane emission and whether it's going to increase or decrease with climate change?
Yeah, I'm only working on the wetland emissions. So I use some kind of climate scenario predicted by climate models. So I run my model to estimate the future methane emissions. So in general, in my case, the methane emission from wetland will increase as a result of global warming. But there can be very uncertain in the impact of land use change or some precipitation change. So it's very difficult, but that's very challenging task. Yeah.
Thank you. So I think we're coming up to the time. I think for the final question, perhaps, I think several of you have been involved in GCP for many years. Yeah. If you could share some of the experience in involving in GCP, the difficulty in collaborating across the nation and, time zone and all this. And how would you, I understand there's many young scientists also attending today's meeting. So, how a young scientist would like to involve in such a network in the future, how would you advise them? Yeah.
Mir?
Yes, Saikusa-san, perhaps start with you.
Myself? Okay. Actually speaking, I have not been working for Global Carbon Project directly, but from my point of view, I'm a little bit out of Global Carbon Project, but I can see that Global Carbon Project is really a good project, one of the best international projects, I think, from the point of view top science, high scientific level, and the leaders of the Global Carbon Project is working very hard to grow young scientists and writing papers. And the grow young scientists by training. In the same time, they very well train young scientists in their project. So that is a point I'd like to say. Global Carbon Project is a really good project, and I'd like to suggest young scientists to join with this community. And for the senior class scientists or the scientists who got permanent job, I'd also like to encourage them to join with the leaders group. For example, Shamil-san or Praveen are already leading international project in many aspects, and of course today's speakers also. And I would like to bring more next generation scientists to work more actively in international community work. That's all. Thank you. Of course, it is a hard work, but we have many good specialists who can advise.
Yeah. Thank you. Anyone else would like to add, or?
No? So yeah, I just want to add maybe a few things, small things. Just support that. Yes, I think we really need the young people because they have fresh ideas and of course, and GCP or the structure of GCP basically quite open. In some sense, that every community announce these things that we are collecting contributions, or we are trying to. Let's say, I can talk about the inverse modeling, the top-down kind of group. So how you operate is that we actually have a community, which is called Transcom. So we have the announcement that we want the GCP methane, it's going to be released in 2 years time, and we are now promoting this inverse modeling activity, and please come and join and contribute. This is how the community has been growing and has been so effectively operating together, and it's going from strength to strength. So I think the new people are coming well, and yeah, it's an opportunity for you to come and join the ladder somewhere and start climbing. So it's a good place to get involved and learn a lot of things in a quick time, because a lot of discussion happens. We know what are the problems in the field. You know where we can invest more time to improve our understanding as a community. So these are things what you gain by joining this group, big groups. You understand the top-notch science where you have to invest more time than your own research. Of course, we should do both. Yeah. Yeah. Thank you.
Thank you, Prabir. Okay, any final remark? I think we are already over time, so if not, I would like to thank everyone, the panels, the attendants, also the staff behind who's supporting making this event possible. So please go to our website to keep following the activity that will come up. We have many exciting events that we'll be announcing in the coming months or so. So please watch this space. And yes, I thank you again for attending this meeting.